Hello everyone. Today we will explore one of the fundamental principles of electromagnetism, Faraday's law of electromagnetic induction. This law is the cornerstone of many modern technologies, from electric generators to transformers or even wireless charging systems you might use. We have already seen that an electric current generates a magnetic field. This, which we have studied through Savart and Ampere's law, was first observed by Hans Christian Ørsted. Also in the early 19th century, brilliant Michael Faraday, an English scientist, conducted a series of brilliant experiments. He wanted to understand the relationship between electricity and magnetism, following the discovery by Ørsted. Faraday's key insight was the reverse. Could a magnetic field create an electric current? His experiments in 1931 revealed the answer was yes, and this discovery laid the foundation for much of our modern electrical technology. To grasp Faraday's law, we first need to understand the concept of magnetic flux. Imagine a magnetic field represented by lines passing through a loop of wire. The amount of magnetic field passing through the loop depends on the strength of the magnetic field, the area of the loop, and the angle between the field lines and the loop. Mathematically, magnetic flux phi is given by phi equal to the dot product between the magnetic field and the area vector. The area vector is a vector whose magnitude is the surface area and points perpendicular to the surface area in question. Phi equals to b times a times the cosine of theta, where b is the magnetic field strength, a is the area of the loop, and theta is the angle between the field lines and the normal to the surface of the loop. Faraday realized that when the magnetic flux across a surface area defined by a ring of conductor changes over time, something remarkable happened. An induced electric current appears in the conductor. Faraday's law states that the induced electromotive force in a circuit is directly proportional to the rate of change of magnetic flux through the circuit. In mathematical form, epsilon is minus the time derivative of phi sub b. Here, epsilon is the induced EMF, phi sub b is the magnetic flux. The negative sign tells us that the direction of the induced EMF opposes the change causing it. Faraday realized this by repeated and consistent experimentation with an immense number of magnets, currents, coils, and so on. And he concluded that it is the change of magnetic flux, the one that induces the EMF. Let's examine what this means in practical terms. There are three main ways to induce an EMF in a loop. Changing the magnetic field strength. For example, moving a magnet closer to or farther from a loop. Changing the area of the loop. For instance, if the loop's size or shape changes over time. Changing the orientation of the loop, rotating the loop relative to the magnetic field. The negative sign of Faraday's law, also known as Lenz's law, states that the direction of the induced current will always oppose the change in magnetic flux that produced it. What are some real-world applications of Faraday's law? Electric generators. By rotating a coil in a magnetic field, generators produce electricity for homes and industries. Transformers. Faraday's law explains how changing current on one coil induces a voltage on another coil, enabling efficient power distribution. Induction cookers. These use rapidly changing magnetic fields to generate currents in cookware, heating it directly. Magnetic induction charging, wireless chargers for phones, rely on Faraday's law to induce current without direct contact, or even toothbrush. Let's walk through a quick example. A circular loop of radius 10 centimeters is placed in a magnetic field of half a Tesla, perpendicular to the plane of the loop. The field decreases uniformly from 0.2 Tesla in 2 seconds. What is the induced EMF? The induced EMF is 4.71 millivolts. To summarize, Faraday's law describes how a change in magnetic flux induces an electromotive force, a phenomenon at the heart of countless technologies. Its practical importance cannot be overstated, as it underpins power generation, communication systems, and much more. Thank you for your attention. Let me know your questions in the comments below, and may science be with you.